Hi, we're Group 7, and our project is on aircraft loading optimization. So we went through this in the interim, and we basically had three subsystems: revenue, logistics, and mechanical fighting each other for maximum profit. So on a system level, this is our goal, and we're not considering fuel or other factors. So in the beginning, we were thinking of putting all three subsystems into one big linear programming problem, but we soon found out that mechanical is more of a feasibility check, because when it says go, we get full profit, but when it says no go, the plane is not going anywhere, and we get zero. So then we thought we should at least bundle logistics and revenue, but we soon found out that revenue is being so dominant that no matter how hard logistics screamed, revenue never listened. So we eventually decided to reformulate the problem by raising the revenue subsystem into a system level, but it must also go through logistics and mechanical subsystems feasibility check, which they will be given with knobs to challenge and affect revenue subsystems decisions. So here are the design variables. We basically want to figure out what passengers and what cargoes to take. And here are some intermediate variables with labeled with color to show which subsystems they are linking. And this effective packing coefficient eta here is the knob we gave to logistics and mechanical to affect revenue. So here are some parameters that we use. And in the constraint, you will see that in the loading limit, we have this eta term added. So what does this eta do? Well, the revenue subsystem is always trying to maximize revenue. And when this eta is set to 1 initially, the revenue becomes really greedy, and it suggests a very optimistic passenger and cargo list to logistics. And now logistics, they have their own concerns, so they will reject some items. And the idea here is that when a lot of items being rejected, it's probably because the suggested list is pretty bad. So it triggers this feedback loop where ADA is being reduced, basically telling revenue you're being too optimistic, come up with a new list. And a similar knob is being given to mechanical, so that only when both logistics and mechanical are happy with the result, when we will return revenue and labor hours to calculate the final profit. So looking at our model as a whole, it's basically the analytical MILP back when revenue was still a subsystem, but now modified with this heuristic feasibility check.
On this slide, we show the modeling approach for each subsystem. First, the revenue subsystem, whose goal is to maximize revenue generated. We assume that each passenger weighs 136 kg with bags which occupy cargo space. The main decision variables are the number of passengers across classes, the binary cargo variables, and the number of containers and pallets. We define the variables and parameters, the constraints, and then populate the model using the aircraft weight and cargo space limits. The logistics subsystem uses an analytical model to minimize labor hours. We assume each bag weighs 16.5 kg and we can fit 128 of them into a container. We assign bags to the forward compartments first and assume a fixed labor and overtime cost. To model the system, we take the number of passengers and cargo units from the revenue system, generate the same cargo list, and compute the bag weights. We then allocate bags based on our earlier assumption. For the mechanical system, we aim to minimize deviation from the plane's reference CG. We opt for another analytical model, assuming that cargo weights and totals are logged in. We model by defining the passenger versus cargo row locations and then computing the CG contributions from them. We apply safety spacing and weight constraints and finally optimize this configuration. For the revenue subsystem, our fares are as displayed. The constraints verify that all bags can be fit into containers and other cargo into pallets. They also check that the total weight limit is not exceeded and that all cargo can fit inside its allotted space. The logistics subsystem uses labor hour coefficients calculated as per the slide and follows the same constraints as the previous system. An additional constraint has been placed on the forward and aft compartment weight limits. The mechanical subsystem uses a component-based CG calculation, which shows the equation on the slide. We place constraints on each passenger per class needing to be seated. Cargo constraints follow no overlapping, pallets taken up, consecutive spots, and cargo being bound by aircraft dimensions.
Use mixed integer linear programming in MATLAB, specifically the inline proc solver, because it efficiently handles matrix-based problems and gives globally optimal solutions for discrete decisions. The revenue and mechanical subsystems use ILP while logistics uses custom heuristics. After the interim report, we replaced the mechanical genetic algorithm with an ILP, which efficiently handles integer decisions for our problem size and mathematically guarantees an overlap-free fit. Our key enhancements include using an efficiency parameter eta, so if packing is inefficient or CG constraints are tight, the system iteratively adjusts the solution. And we also linearized the nonlinear center of gravity objective using an auxiliary variable so the ILP could solve it instantly.
Runs. The table reports the optimal decision factor X star, where the entries are passenger counts, AMF containers, pallets, and selected cargo items. And F star is the maximum revenue from the profit subsystem. The main pattern is that business and premium passengers are always full, so the model treats those as high value amount. Most of the changes happens in cargo selection and economy passengers. When the pallet cap is reduced to 5, the model keeps the passenger allocation the same but selects fewer cargo items, so revenue drops. When the pallet cap is increased to 7, the model shifts more capacity towards cargo. Cargo selection increases, but economy passengers drop, so there's a trade-off between cargo revenue and lower value passenger capacity. The volume relaxed case gives the highest nominal revenue, but it also creates the largest mismatch with logistics, so it is less realistic downstream. Finally, when the payload limit is reduced to 50,000 kilograms, the solution mainly cuts economy passengers while keeping business and premium full. So overall, the results show that cargo selection and economy passenger count are the most sensitive parts of the solution.
Post-optimization, we have found 3 active constraints within our system, for which we have conducted a sensitivity analysis on. Our most sensitive constraint is the max cargo station constraint, indicated by the station limit parameter. Due to aircraft mechanical characteristics, there are 4 different cases in how we may perturb this constraint. For all 4 cases, we have found a similar constraint sensitivity coefficient of 746. Next up is the max pallet cargo capacity constraint, indicated by the pallet volume limit, which has a sensitivity coefficient of 557. Our least sensitive active constraint is our max payload constraint with a sensitivity coefficient of 3. All these constraints limit how much cargo we can admit onto the aircraft, which is a main source of revenue. Thus, it makes sense that the analysis shows that the constraints which have large changes to cargo holding capacity to be the most sensitive. After the constraints, we also conducted a sensitivity analysis on parameters related with passengers aboard the aircraft. Our most sensitive parameter is the passenger weight, which is split into carry-on bag, check-in bag, and body weight. This parameter also directly affects our optimization function as lower weight causes passengers to be more profitable than cargo from a revenue per kilogram viewpoint. The next parameter is ticket fares, which are direct sources of revenue. The sensitivity of ticket fares is directly related to the number of seats available in the aircraft. Finally, the bags per container parameter is tested and found to not be very sensitive.
For our reality check, we validated the system optimizer's output against industrial data. Our system revenue of $435,000 per flight falls within the range we estimated from the ANA's FY 2024 annual report, and our cargo share of 32% align within reported for Asia long-haul carriers. For logistics, the optimizer's 18.5 tons of belly cargo matches typical 15 to 20 ton load on Trans-Pacific 787-9 routes, and our turnaround time is consistent with industrial benchmarks once you account for parallel ground operations. On the mechanical side, our CG index is near 0, which is exactly what airlines achieve through standard weight and balance dispatch. The main discrepancy is our 100% load factor versus ANA's real 79.2%, so our result represents a best case ceiling. This slide compares our interim system result to the integrated system at $20 per hour wage. The headline volume, not weight, is the dominant bending constraints. In profit, the system adds 2 economy passengers but drops 7 cargo items, reducing revenue by about $7,300. Because when logistics pack a cargo per pallet with the volume limit, only 101 out of 104 items actually fit. In logistics, labor hours stay locked at 35.08, identical to interim. The Pareto front is flat across all wage rates because volume locks cargo selection. In mechanical, the CG optimizer achieved near perfect balance. The system now has 720 kilo of weight slack, but volume prevents using it. The main takeaway is that the three bending constraints: weight, per pallet volume, and stations. Three engineering interpretations from our system optimum. First, the optimal configuration is unique and robust, invariant across all wage rates from $0 to $5,500 per hour. First, the optimal configuration is unique and robust, invariant across all wage rates from $0 to $500 per hour. No revenue labor trade-off exists because per pallet volume locks cargo selection. Second, weight capacity is the most valuable resource. Sensitivity shows $1,370 per 1% change in the weight limit. A 5% increase enables roughly 19 more economy passengers. Third, the two-stage architecture introduces a 3-atom gap between selection and packing, leaving a few $1,000s on the table. For future work, a single-stage integrated MILP to eliminate the gap. Dynamic pricing. For future work, a single-stage integrated MILP to eliminate that gap. Dynamic pricing coupled with real-time demand and fuel burn linked to CG position for a more physically meaningful trade-off. Thanks for watching our presentation. That will be the end of the presentation.